Good morning to all. Dr. Kulin. Dr. Kulin,
Hello, sir.
am I audible?
Yes, sir.
Okay, you can continue. Okay, you can start. Yeah?
Okay.
Hello. Can I start?
So, wait, sir.
So today I am Dr. Priju from CWRDM, Calicut. So I would like to present. Today I am assigned the topic
Dr.
managed aquifer
Priju,
media.
Dr. Priju, just a moment. Just wait,
Okay.
please. We will tell you. Okay, to continue. Okay, just wait. Dr. Kulin.
Hello, sir.
Okay, you just start. Actually, dear participants, please wait 2 minutes. There's some technical problem here. So you just wait for 2 minutes. Sorry for the delay.
Hello, am I audible to everyone?
Yeah.
Yes, Ashwati.
A very pleasant good morning to all. Welcome to ENVIRON 2020 National Online Lecture Series, Day 4 Final Session, which is hosted by Department of Geology, Sahadev College of Advanced Studies in association with Center for Development, Environment and Development, Trivandrum. Thank you all for joining with us for the final section in this lecture series. It is my pleasure to invite Dr. Lindo Alapad, Head, Department of Geology and Environmental Science, Christ College, Irinalakuda, for the felicitation.
Good morning, everyone. Hello, am I audible?
Yeah.
Yes, sir, we can hear you.
Okay. Yeah. So thank you, sir, for the kind invite to give felicitation for the event. I'm glad that Sahadev College of Engineering Advanced Studies is organizing such a very instilling meeting on different aspects of geoscience. You have all these days, we had 4 sessions, mainly dealing with different spheres of Earth. So we had a talk by Mr. Anup from GSI, who was talking about remote sensing and GIS and its applications. Then we had Dr. Ramachandran from NSIS, former scientist from NSIS, and also from the KSDMA and the KSCSTE, who was talking about land-based studies, basically on environmental degradation leading to landslides in Western Ghats, and a former director of GSI Mangalore, Mr. AC Dinesh. He had talked about marine sediment distribution in world oceans, and today we have some other aspect, that is subsurface aspect of our geosphere, that is managed aquifer recharge. So I first of all I congratulate Department of Geology of Sahardia College of Advanced Studies in the able leadership of our Davis sir. He has done excellent work throughout the year, and I'm very glad that last year you were also able to secure a rank in the university examinations with many institutions competing for the same. So I congratulate all the faculty, Davis sir, Dr. Kulin, Ms. Ashwati, and Ms. Asba. So I'm sure that your hard work and systematic approach and the efforts to uplift the students that has resulted in getting such a wonderful result in the university examination. And it is yet another interesting moment or proud moment that Sahardia Department of Geology of this college has come out in a national level, organizing webinar in very important aspects covering all spheres of life. If you see that you have a space-based observation, oceanic observation, or oceanic studies you had talks on, and terrestrial aspect, and also subsurface aspect. So with this, it covers a complete comprehensive overview of our geosphere, and certainly I'm sure that there are many more such initiatives to come, and this is just a beginning, and there are miles to go for betterment and further and establish this department as one of the best department in Kerala and on the all India basis. So I wish all the best to all the participants, and also to the department. Like this, though it has started recently, but that the department has made the mark in the geology community of the state, and also now into the country. So I wish everyone the best. And to say a few words about the speakers, I know that two of the speakers of this webinar series, Mr. Anup and Dr. Priju, both of them were our alumni, and it is very, I'm very glad to see that our alumni are coming to such highest positions in giving seminars and a national webinars. So that is also a proud moment for us being a part of the Christ community. So, and our head of the department of Sahardia College is also from our alumni, and it is befitting that we had this alumni meeting that we have put today. So it would be heartening to see that our alumni doing good in giving expert lecture in different areas. So Dr. Priju is a very eminent scientist in areas of, he had done a lot of work in the initial stage on the coastal geomorphology and sea level changes. And after that, he has joined at CWRDM, and now he is active researcher in areas of groundwater studies. So it is truly a blessing that you have such an eminent speakers for the webinar, and I wish everyone the best, and wish you all the best. Have a fruitful session. Thank you, everyone, and once again congratulate everyone for organizing such a wonderful session. Thank you, bye.
Thank you very much, sir. Now we'll move on to our fourth and final lecture, Managed Aquifer Recharge by Dr. C P, Scientist, Groundwater Division, Center for Water Resource Management, Calicut. Before that, a reminder to everyone, please join cameras and microphones for the smooth conduct of the session. And if you have any doubts during the session, type your questions in the chat box. Also, attendance is mandatory. You have to fill out feedback form, which will be shared at the end of the session. Now, I invite Mrs. Ashpa Binoy, Faculty, Department of Geology, to introduce our resource person.
Good morning, one and all. I would like to introduce today's presenter, Dr. C P Priju, Scientist, CWRDM, Kozhikode. He has secured doctorate in marine science from Cochin University in coastal geomorphology and sedimentology. By His Excellency, he has secured positions like hydrogeologist, lecturer, DST young scientist, and scientist. He has published almost 20 publications till now. We had loved to hear from you, sir. Welcome you to the presentation. Thank you, sir.
Thank you very much. First of all, I thank Head Department of Geology, CWRDM College, for inviting me for this lecture. I also thank Dr. Linda Alapat, Head Department of Geology, Christ College, for the facilitations. So we will move on to the topic, Managed Aquifer Recharge. Today I am entitled. So managed aquifer recharge is nothing but artificial aquifer recharge. It is an engineered system which is designed to recharge excess water, and that can be reused later for the betterment of the system. So artificial recharge, process by which the groundwater reservoir is augmented at a rate exceeding natural replenishment. And managed aquifer recharge is the enhanced aquifer recharge or augmented recharge. It is any engineered system which is designed to introduce and store water in an aquifer, which is intentional storage and treatment of water in the aquifers. And there is another term, incidental recharge, that recharge reaches an aquifer from human activities not designed specifically for recharge. So this is the one schematic example of the managed aquifer recharge by injection or infiltration. You can see the injection well in the middle and the abstraction well in the right hand side. So this is a typical example of the managed aquifer recharge. There are other some terminologies like ASR, aquifer storage and recovery, where the stormwater is led to the aquifer in wet season and recovery from the aquifer in dry season. You can see the black and red lines, which is a cone of depression, cone of elevation, depression in the aquifer. And injection wells, it is also a system where the water is injected into the rivers to the aquifer under pressure. So when we talk about the recharge, we have to see the vertical cross section of the aquifer, how we encounter when we go deep. So whenever the rainfall or water is percolated, first process is called infiltration. It happens in the topsoil zone, and it is followed into the vado zone where percolation is happening, and is leading to the piezometric that zone and recharge to the groundwater. That is, so it is reaching to the water table. The water below the water table is saturated, it is in the saturated zone, and it is called groundwater in our terminology. So recharge is a function of area, time, and permeability. The contact between water body and ground surface, and making effort for creating more permeable zone for accelerating recharge to the groundwater. So when you can see the left hand side, post-monsoon water level and pre-monsoon water level, that we have to account. When it is large, that difference water level fluctuation is large, that is the zone where we can recharge more water. Or vado zone is more. So rechargeable groundwater is utilizable resource, we can say. So we have to take into account the draft groundwater. So trend of groundwater is a function of the draft and rainfall. So why artificial recharge is required? So we are getting enough rains, but we need artificial recharge even then. Due to our Kerala is having steep topography, within 48 hours, the rain, a drop of rain, it will reach the ocean. So, and we have the short spell of rain, high intensity rainfall in the monsoon, as the southwest monsoon and northeast monsoon. So beyond that, we don't have the rains. So here we can see in this slide, so change in groundwater is the input inflow and minus outflow, or input minus output. That is change in groundwater, GW, is the addition. You can see recharge from precipitation, recharge from surface water bodies, recharge from canals, recharge from surface water irrigation, recharge from groundwater irrigation, and it is minus the outflow, it's the groundwater inflow, groundwater discharge to the stream or spring, evaporation losses, groundwater extraction by pumping, groundwater outflow. So whenever this is less, we have to go for recharge, input minus output. So here it is shown the hydrograph, that is our trend of water level trend. So it is showing decadal water level trends, or monthly water level, or yearly water level trend. You can see the top hydrograph is showing the water level is depleting, and the bottom one water level increase, or water level. So here where we have to recharge is the trend of water level is depletion. So while planning the recharge, we have to go systematically. We have to first identify the area where we have to recharge. Investigation of the area has to be conducted, and the detailed project report of the watershed. The unit of recharge we do is normally watershed. The identification of area, the problem, we have to identify what is the problem, whether water table depletion, groundwater level depletion, or sustainability problem, or quality improvement has to be done, whether arsenic problem is there, chloride, iron nitrate, sulfate problem, seawater intrusion. So we have to identify what is the problem of our area, and we have to demarcate the area. Catchment area is better than the artificial recharge for the groundwater, and we have to calculate the Vado zone. The Vado zone thickness is more, we have more prospects, and availability of recharge water is very important. How much rainfall we are getting, how much we can commit for the recharge, and suitability. So demarcation of the area. So here we are applying GIS techniques. The base map, we have to prepare catchment, drainage map, soil, physiography and geology, and depth water level map. That 10-year or decadal post-monsoon depth water level map of 3-meter interval have to be prepared. The long-term water level trend, the decadal post-monsoon water level trend map has to be prepared. So this is an example of Harun River in Chhattisgarh. You can see this watershed. The catchment may be micro, macro, or mega size, depend on the extension of the problematic location. We need not go for entire area for recharge. We need to go to the recharge area, or there is when we do recharge, that is helpful to the aquifer, the replenishment. The entire area is not required for artificial recharge. So this is the decadal post-monsoon water level. You can see the legend 0 to 3, 3 to 6, 6 to 9 meter water levels in the yellow, green and blue color. So this is the decadal post-monsoon water level trend and trend. You can see there are 3 divisions showing either water level increase in the top portion, there is no change in the middle portion, and there is a depletion or decrease in the bottom portion. So we rise or no change or fall. Where we have to target is the falling water level area. So this is the area we have demarcated based on the water level, where there is no change, and where there is a fall in water level, we have targeted in the GAS. So we not only we have to consider this water level, the aquifer is made up of the geological materials. We have to consider the geology of the area, whether the geology of the area is suitable for recharge, where we have targeted. This this showing the massive shale and limestone formations. Limestone is better than the massive shale. So we have further demarcated the area for artificial region, blue patches, where falling water level, and we have omitted the massive shale portion of the this area. So finally, you can see the where we have omitted the vertical lines, the area we have omitted, and rest of the area is selected for recharge. And the structures are shown, the surface dikes or boulder check dams and percolation tanks. That is shown in along the this stream courses. So we have the decadal, post-monsoon water level, and trend is also in the Kharun River Basin. So calculation of Vado zone, how we can calculate the Vado zone in an aquifer. So storage space is that area into thickness into the average specific yield in MCM. So A is a demarcated area for artificial recharge. B is the post-monsoon average depth to water level, 3 meter in every zone, and C is the specific yield of the particular formation. So this is the name of the watershed is Gajara watershed. 250 square kilometer area total. Out of that area identified for the artificial recharge by that is 153 3 to 6 6 to 9 60 square kilometers, and we have multiplied it with the post monsoon average depth to water level 153 into 1.5 to 30, 16 to 4.5 to 70, so 500. So into average specific yield 0.02 is the average specific yield of the formation. Total storage potential as volume of water is 10 MCM. So this is the calculation of the Vado zone. So next is how much surface water. Water is surface water during rainfall, how much it is required, or the canal water or whatever it may be. The stored water, say 100%, the loss of soil moisture and leakage 25%. So net water available for the recharge 75%. So the reciprocal we have to take, it is 1.33. And surface water requirement we have calculated storage space into the reciprocal of the required water, that is 13.33 MCM. So this much water is required to recharge the watershed. So source water availability is assessed in terms of non-committed surplus monsoon runoff, which as per the present water resource development scenario is going away unutilized. And this component can be assessed by analyzing the monsoon rainfall pattern, its frequency, number of rainy days, maximum rainfall in a day, and its variation space and time. The variation in rainfall pattern, space and time, its relevance in relation to the scope for artificial recharge to subsurface reservoirs can be considered for assessing the surplus surface water availability. So all this component has to be assessed by analyzing the rainfall pattern. So non-committed surplus monsoon runoff, we can, its availability space and time is, can be calculated by river gauging or some formula, applying some formula. So the rainfall runoff, it is estimated by Stanger's table for the average monsoon rainfall of the area. The average monsoon rainfall of the areas we have, this is Chhattisgarh, it's a less rainfall area, 1158 millimeters. The percentage of runoff to rainfall as per the Stanger's table, the depth of runoff due to rainfall is 40.3 centimeters. Total yield of the runoff generated from the watershed having 20 to 50 square kilometer area works out to be 100.75 MCM, and 30% of the total runoff is 30.225 MCM is considered as surplus monsoon runoff available for artificial recharge. So other sources we have for recharge is canal water or trans-basin water if available. So suitable recharge structures we have to design. So we have the storage distribution, 70% we have to give that for earthen structures or percolation tanks that is designed in this area, that is surface spreading techniques, and 30% is cement plug or concrete RCC where bank storage it is the technique, and density of structure to be realistic per square kilometer and entire affected area of watershed to be benefited. So drainage, physiography, soil, geology, and position of aquifers are all governing important role for suitability of artificial recharge structures for groundwater recharge in any area. So this is the infiltration rate curve. You can see whenever we have rains, what is the infiltration rate? There is a question. Infiltration rate varies different by soil or depending on the geological properties, it varies. So you can see the red line, infiltration rate gradually decreases and then increases as the number of days increases. It is decreasing due to deposition of particles, algal growth, and colloidal swelling. So infiltration rate is shown as meter per day. So investigation, we have to carry out this investigation before going for artificial recharge application. So soil properties, physiography and geomorphological map we have to prepare, hydrometeorological and hydrology we have to consider, geophysical application we have to do to understand the subsurface. Especially suppose we have the lineaments or dikes, that is important, and hydrogeology is the formation characteristic we have to see, whether there is a in the geological material, the feasibility structures we have to design, the civil engineering consideration, the structures we have to make it to the design, the beneficiary group whom we are doing recharge, which beneficiary group is benefited, and economic consideration we have to see. Actually, this Karun River or Gajra watershed, this Central Groundwater Board has prepared this all this feasibility report, and they have implemented 200 crore rupees project in that area. So when we see the artificial recharge, where we have to recharge, particularly in Kerala, we have the steep topography. Whether we go for extensive recharge project in the coastal plain or lowland regions, or we have to target the recharge zones. Recharge zones where the exact area we have to target. You can see the cross section where recharge zone and discharge zones are shown. Recharge zone is the area where recharge is the prominent process. Recharge can happen, and discharge zones mainly the water is going out or as a discharge. The discharge zones where the most of the wells are located, or water is discharged into the streams and finally in the wetlands and oceans. So what is the rate of recharge? This is the recharge as per the natural system. So the rate of recharge, as you can see in the right hand side, a stream is shown. It can be days, or it can be years, it can be centuries, or it can be millennia. So whenever we are taking out water, so we have to consider this. So the recharge can happen depending on various factors. It can be based on the confined and unconfined. You can see the confining bed in this figure, where that will not permit the downward infiltration of the water. Confined bed may be a clay layer, so it will take a millennia to have recharge. If we take a confined well from a tube well which tap confined aquifer, so it will take millennia to recharge unless we do artificial recharge in that confined confined aquifer. So recharge systems. So all the downward arrow showing the recharge, and upward arrow shows the discharge or taking out. We have irrigated agriculture, wildlife refuge, recharge basin, treatment plants, municipal industrial use, water treatment plants and reservoirs. All this shown as interconnected system, and downward we have the confined aquifer and confined aquifer systems. So artificial recharge methods, it is broadly divided into direct methods and indirect methods. So we have the direct methods, surface spreading techniques and subsurface techniques. So surface spreading technique, there are many. This is widely used for recharge, flooding, ditch and furrow method, recharge basin, runoff conservation structures like gully plugs, bench terracing, contour bend, small waves, percolation tanks, and we have the stream modification, surface irrigation. These are commonly used, and subsurface techniques like injection wells, we have seen recharge wells, and indirect methods are induced recharge, aquifer modification, groundwater conservation structures. In induced recharge, we can increase pumping well for that will induce the recharge from a stream, collector wells, infiltration galleries, which will all induce the recharge from a stream. The aquifer modification, bore blasting. For example, if a bore well has no water, you can apply, you can blast the bore well to have recharge. And hydrofracturing, applying the water pressure, you can try recharging the aquifer. In groundwater conservation structures, we have groundwater dams of bandaras and fracture sealing, some of the advanced methods of indirect recharge methods. So surface spreading techniques, we have some conditions. The aquifer to be recharged should be unconfined and sufficiently thick to provide storage space. The surface soil should be sufficiently permeable to maintain high infiltration rate. The viaduct zone should be permeable and free from clay lenses that may cause perched water conditions. And groundwater levels in the phreatic aquifer should be deep enough to accommodate the water rise and avoiding possible waterlogging conditions. Aquifer material should have moderate hydraulic conductivity so that they recharged water retained for a sufficiently long period in the aquifer can be used at the time of need. And topography plays an important role in controlling the recharge rate. The areas with gently sloping land without gullies or ridges are most suited for surface water spreading techniques. So this is a flooding technique. From a stream, you can see it is diverted and it is flooded, and that space and time it is used for recharge, and uh, the water remaining is collected in the return canal again to the stream. So the spreading surplus surface water from canals or streams over large areas for sufficient length of time to recharge the groundwater body. The water conserved in this groundwater storage can be pumped for augmenting canal supplies during summer or to provide irrigation water to the adjacent areas. So this is another ditch and furrow method, suitable areas with irregular topography. Shallow, flat bottom and closely spaced ditches or furrows provide maximum water contact area for recharge water from the source stream or canal. It requires less soil preparation than the recharge basins and less sensitive to silting. So these are other some of the techniques. Stream water is diverted to feeder canal ditch, from which small ditches are made at right angles in the lateral ditch pattern. And dendritic ditch pattern, water is diverted from the main canal to a series of smaller ditches spread in a dendritic pattern. And contour ditch pattern bottom is diversion structure is shown. Ditches are excavated following the ground surface contour of the area. So direct recharge in shallow and deep aquifer. So the direct recharge in shallow aquifer is shown in the top, and the ditches are shown and drains are shown. Drains will take out take out water. Ditches will recharge, and surplus water is taken by the drains. In the bottom is the drains with boreholes as a recovery method. So through boreholes, the recharge water is taken. So this example of showing recharge basin, you can see from the stream, it is a series of basins are constructed, and water contact time is longer for the stored water. Suspended material in the stored water, source water is reduced as water flows from the upstream basin to those below. Periodic maintenance such as scrapping, etc., we can do to restore the infiltration rate, can be done by bypassing the basin concerned. So we allow the water in the basin to recharge. If we have enough space, we can follow this method. And in the coastal aquifer, there are recharge methods to control the salinity intrusion. So coastal aquifer, we have the freshwater saline water interface. We can push the interface towards the seaward by recharging. So this is an example showing the groundwater recharge in the coastal zone. You can see the clay that is acutard and aquifer. This is a common that geology is seen in the coastal zone. So next, runoff conservation structures widely used. So this need to be increase in this will increase the availability of groundwater, enhance the sustainable yield of aquifers, improve quality of groundwater through dilution, arrest declining trends of water levels, prevent depletion of groundwater reservoirs in the area of overexploitation, decrease floods on local and regional areas, reduce pressure on storm drains in urban areas, enhance the quality of the environment. So this is the some of the methods. Contour bunding, you can see the bunds are that is made along the contours. And terracing will help in recharging of the aquifer. We have the percolation tank where water is flowing water is with bund. We are the top figure, the wells are constructed downward side of the bund where water is taken out. So we have less permeable soil is used for the construction of the bund and permeable soil beneath. An example is shown from Kozhikode. This is an RWH pond in the near to our campus in IAM, where all the water in the area is diverted and collected in a large pool where they are using their needs are catered. And bottom is you can see coconut grove, the RWH in rainwater harvesting, the plantation is practiced. So roof water harvesting. Roof water is diverted to some pond, and if it is infiltration pond, we can get the water in the downstream portion. So this is in the medical college where it happened to be an infiltration type of pond, intake well over downstream side of the pond. The recharge pit, we have a recharge bottom, we can construct a recharge pit. And where some ponds, we have even the bottom low permeable material, we can construct some shaft to divert the water to the permeable material or to the water table. So in the coastal zone, we have a narrow land with a large coastal area, coastal zone. Coastal ponds this is in the Kodungalur area where you can see coastal ponds are extensive, or even the south towards Alpi region also coastal ponds are widely seen. This will reduce the salinity of water and it will recharge the that sandy aquifer. So coastal ponds which control the groundwater salinity. So this is a method where saltwater intrusion is controlled by the recharge well. So in the middle you can see the recharged well, and the right hand side production wells where water is taken out. So left side there is saltwater freshwater interface which is pushed towards the seaward using the recharge well. This is another example. It's commonly used, especially there is an agency called Malpolima which recharge the wells, especially in the Thrissur district. They have done different implications. So you can see the roof water is diverted to a filter pit, and it is filtered water is recharged to the directly into the open wells. So recharge to the abandoned boreholes. You can use the boreholes, abandoned boreholes also for the recharge purpose. So the care is to be taken to filter the recharge water. Otherwise, it will contaminate the deep aquifer also. So recharge to the trench. You can in the houses, buildings, you can construct this type of trenches, and in some filter bed you can put, and the water can be diverted to these trenches for the recharge purpose. So this is the gravity head recharge well or borehole, where the water is from the roofs are diverted to injection wells after the filtration. So this is an example from Coimbatore, Tamil Nadu, where some of the houses they use boreholes, as well as it will recharge the roof water to the borehole with the filter bed. So this is another recharge pit considered for a bore well, and right hand side it is showing it is recharge, even the roadside drain they have constructed a recharge structure to the aquifer. So this is these are two techniques, ASTR and ASR. ASTR means aquifer storage, transfer and recovery, where one well it is recharging, another well taking out. And aquifer storage and recovery means the same well we are recharging and we are taking out the water. So when surplus water is available, these techniques are used. So river water is diverted to the aquifer, applying some pressure. So you can see the downside photographs showing applying pressure, how they are recharging the aquifer. So this is the typical example how the movement of ground the subsurface. So there are fractures. It depends on different parameters like geology, type of structures. So you can see the arrows showing the water is how it is flowing in the subsurface. So earth dams, we have earth dams like Vajani Dam, Priju district, Banasira Sagar Dam in Wayanad. So earth dams are widely useful for recharging the water. Some of the establishments they are using earth dams for that we have seen the percolation tanks that there are these are minor earth dams. The bottom is showing right side, it's a Vayani Dam. There is a clay core which is impervious for the earth dam. Another is sand dam. This is not common in our area. It is in North India. The sand dams are there. You can see the layers of sand deposited during rainy season, which will arrest the ground, the water flow, and it will recharge the aquifer. This is the simple check dam which control the water. A check dam with gears, PCB. This is another example from the Coimbatore area, where it's a type of check dam cum percolation tank, where they recharge this water for deep infiltration, where they have bore wells which will take the water. This is from highland areas like Ooty, how they are collecting water for the plantations. This is from Bharatapura, where there is a check dam weir is shown across the river. Another type of dam is clay dams. We can use clay dams where clay will arrest the flow of water. So water is trapped in sand that can be used. So subsurface clay dam. This is subsurface masonry dam. Instead of clay, masonry dam can be concrete wall is made where the water is trapped in sand. A well is shown in the upstream side. So this is a subsurface dike under construction in Palakkad district under Central Groundwater Board scheme. So there they are using this subsurface masonry work is a dike. Piezometers are shown, that pipes are piezometers where upstream and downstream side water level they are monitoring. There is quite positive effect in the upstream side, controlling the downward flow of the water. These are ponds widely in our state. Ponds are also, this is a groundwater type pond where in Kannur, Karlasheri Temple pond. These are the ponds we have in our area. Laterite or clay, these pits are filled with water. This is also acting as a recharge pond. This is a large pond in Thrissur, Vadakachara, Thrissur city. So all this collect water and recharge in the summer months. The Kerala scenario, if we are taking, so we have the narrow strip of land with 38,863 square kilometer, and that area percentage, if you see, the coastal plain and lagoon, the western side, and highlands and mountain peaks in the eastern side. Here it is shown as lowland and midlands. This area is highly suitable for recharge structures, as well as we can use some of the highland areas for the recharge structures. In the coastal plain and lagoon, almost throughout the year it is waterlogged, so we are not normally considered for the recharge. So stratigraphy, as geologists, we can see the geology of this cross section of the Kerala region. So we have whenever we go for any recharge project or any groundwater related work, the first thing to be considered is the geology. Without knowing the geology, you cannot do anything in the ground. So we have the different type of lithology. So sand, clay, riverine, alluvium, crystalline sedimentaries, and stone, clays with lignite, and so on. So laterites, so gneiss, schist, charnocite, and associated rocks, chondrites. So we have to consider the hydraulic properties of these aquifers or the lithology. We have to consider. So this is hydrogeology. Groundwater occurrence is phreatic, semi-confined, and confined condition. The phreatic aquifers like weather, crystalline laterite, and alluvial formations are seen. And confined semi-confined aquifer deep fractures in crystallines and the granular zone in the tertiary sedimentary formations. And midland aquifers are mainly laterite. We have in our area, this area is laterite mainly, the midland region, 1 to 30 meter thick phreatic condition. And crystalline aquifers like weathered, semi-confined, alluvium, loam, riverine, phreatic to semi-confined. Alluvium is very highly potential compared to crystalline aquifers, and laterite is having high permeability, so it will not store much water, it will pass water only. In some cases, we have laterites good potential. In coastal aquifers, alluvium, sand, clay, marshy, phreatic to semi-confined condition. Tertiary formations are seen in Workale, Koilan, especially in Alleppey area. Workale and Wycombe formation is tapped. That is freshwater zone. In Koilan, Alleppey formation are at a brackish, semi-confined to confined condition. So this is a typical figure showing the crystalline aquifers, semi-confined and leaky aquifer. You can see altrite. Altrite is nothing but laterites, and followed by that weathered zone with the fractures, and below that fracture layers crystalline formation with the fractures. These are the areas where you can see deep fracture, where we get good fracture aquifer in the bore wells, and fresh basement is shown below. The coastal scenario consists generally of typical ridge and runnel. Ridges are sand ridges are the potential areas where we get the fresh water, which is coastal sandy alluvium or runnels with lesser thicker sand, and affected by tidal influx and will not sustain excessive pumping and deep extraction, which result in salinity influx during dry season. Generally, the sand thickness near the coast is 1 to 3 meter only, and it's underlined by black organic clay in most places. And fresh water is available only in the sandy horizon, and in most of the areas, saline water comes inland through the channels. The bottom figure showing cross section of the barrier island, where freshwater saltwater interface is how the thickness of lens is increasing and decreasing, freshwater lens. This is a figure shown earlier. This is another figure we have already seen. So finally, ultimately we have, after the managed aquifer recharge or artificial recharge, we have increase in quantity. We are doing recharge either for increasing replenishment of groundwater. So this figure showing the after start of the recharge, the water level rise with the artificial recharge. So without recharge, there is no rise. Or we do recharge for the quality remediation. After recharge, for example, salinity is reducing. In some areas in coastal region, after recharge, open well recharges, the salinity has come down considerably. So quality improvement in the artificial recharge. The injected water was very fresh with a salinity of almost 4 millisiemen per meter. So this is the some overview of the different artificial recharge methods and indicative capital costs, construction features, the O&M aspects. like percolation tank, recharge shaft, recharge pit check dam, recharge trench, recharge through hand pump, recharge through dug well. So much that financial consideration we have to work out. This is a figure showing ASR and ASTR. This is a future prospect. ASR means aquifer storage and recovery. The top figure showing the same well is used for the inward and outward that it will store water, and whenever it is required it will take water. Whenever we have enough space for storage, we can apply this aquifer storage and recovery. And aquifer storage, transfer and recovery, when we need quality remediation of the recharge water, one well we are using for recharge, another well we are using for taking out water. So this aquifer storage transfer, during this subsurface transfer, that quality is remedied. These are type of ASR systems: recharge basin, Vado zone well, recharge wells. So technical component of managed underground storage. Another important thing in the future is when we have enough space, you can store water underground. So that is called managed underground storage, MEVS systems. So large tunnels like structures, or large area, large aquifer Vado zone we have. So we have to find out and just that water, surplus water, we can direct that source water. Quality, quantity, these are the considerations, duration and reliability. And finally, to the end use, quality, quantity, duration and reliability we have to consider. So we have the recharge in between, recharge method, storage zone and recovery method. These are the three systems we have to do more research and find out what are the ways we can store underground storage can be designed. So major characteristic of aquifer recharge methodologies. So recharge basin, Vado zone well, recharge wells including ASR. So the aquifer type, pre-treatment requirements, estimated major capital cost, capacity, maintenance requirements, estimated life cycle, location aquifer water contact. These are the considerations we have to taken into account. So properties of major type of aquifers. So these are the confined, semi-confined, and confined, including water table, and may or may not be perched. So we have different porosity types in the type of aquifers we have. So finally, the future prospect, you can even recharge the wastewater, and the quality can be remedied and it can be reused. So you can see a concrete chamber, discharge chamber is shown, and infiltration, the time is given for the infiltration, that the quality is remedied in the day 5, and in day 75 it is reused. So this is the future systems, the wastewater recharge. The aquifer can be a good filter for the contaminants. So thank you. So thank you.
Thank you, sir, for the wonderful lecture. It was very informative. Now we will move on to question and answer session. If you have any doubts, type the questions in the chat box or unmute your mic and ask.
Dr. Priju, may I ask one
Yeah.
question?
Yeah.
Now you're talking about a subsurface recharging. What
Yeah.
about underground recharging? I think in Kerala, there are more than 900 panchayat is there. Every panchayat before they made a lot of bore wells.
Okay.
Now most of the bore wells now totally damaged, nobody using. Why
Yeah.
don't you try for the rain harvesting through this bore well to recharge the underground water? Is it possible?
Yeah, there is some technical considerations. We can widely apply recharge borewell, but a good yielding borewell only we can use for good recharge well. That will act as good recharge well. Since the fracture geometry depends, the recharge depends on the fracture geometry, and we need to very carefully recharge the water, divert water after the enough filtration and quality we have to ensure. So that is a good idea. Uh, that has to be done.
Any running project is going on for this project?
The borewell recharge, now it is not encouraged since this consideration are to be satisfied. But in Tamil Nadu, it is done. Our neighboring state widely using borewell recharge. That we have to do in the near future.
Okay, thank you.
Okay.
Sir, there is another question.
Okay.
How can an aquifer be recharged naturally after a drought? I will repeat the question now. How
Okay.
can an aquifer be recharged naturally after a drought?
So, after a drought, normally we have rains. We are expecting rains. So, aquifer will naturally recharge. There is natural recharge after drought, but artificially we can, especially using water conservation measures, like we are practicing agriculture. So agriculture measures are there. We can make pits on the ground. We can have pits and trenches. Already we have different type of water conservation, soil conservation measures. So it will naturally recharge during rains.
Okay, thank you, sir.
Okay.
Anybody else? Then we can proceed next.
Okay, if there is no further questions, that conclude our Q&A session. Now I invite Dr. P.O. Jensen, Principal, Sahardaya College, for concluding ENVIRON 2020 National Online Lecture Series. Over to you, sir.
Am I audible now?
Yes, sir.
Okay,
Yes,
good
sir.
morning, one
We
and
can hear
all.
you.
Respected speaker of the day and head of department, Professor Davies, these faculty members of Geology department and delegates from Sakrudaya as well as from other colleges. A wonderful workshop our lecture series is coming to an end on today with a very good, informative final day speech. We have 4 days of lecture series. On the very first day, on day 1, on 27th, we have a presentation from Mr. Anu, senior geologist, on application of remote sensing in geosciences. In that presentation, we have heard about the basics of remote sensing, fundamentals, and up to the application of remote sensing in geotechnical projects. A healthy discussion was on that day have made, and I think all the participants on that day enjoyed that talk, and they have been informed very well on the topic. On day 2, on 28th, we have the speaker, Mr. A. Dinesh, Director, Marine Coastal Survey Division, on marine sediment distribution in world ocean. On that day also, starting from morphology of ocean floor till the last discussion, he has discussed about pelagic province related to ocean water column and benthic province related to the ocean floor, with a very good schematic diagram. With that diagrammatic representation, even the non-geologist also can understand the topic very well. On yesterday, that is on 30th October, we have the speaker, Dr. K.K. Ramachandran, former member secretary of KSCSTE and KSCSTE-CWRDM, scientist, retired scientist. He was presented the environmental degradation leading to landslides in Western Ghats. He has started his talk. What is an environment? He has taught about environment, basics of environment, till the landslide prone area in Kerala. I have also participated in that discussion about the Kudiran tunnel also. He has replied, or he has discussed that matter in a very good manner. And after that, finally today, our speaker, respected speaker, Dr. Priju C P, scientist, Center for our CWRDM, Kozhikode CWRDM is very much famous nowadays. He talked on the very well, and discussion was going on. This discussion was made, and I think the participants were very much happy about his explanation with a very good diagrammatic and graphical presentation about this topic. So I congratulate Professor or Dr. Priju C P, scientist, for presenting in a nice manner this topic, and all the 3 presenters, they have also done very well. So on behalf of Sakhdaya College of Advanced Studies, I express my deep sense of gratitude to these 4 speakers, and I invite you, when that time permits, when there's this type of online class starts, I invite all of you, especially Dr. Priju C P. Now, I think he may be the only person presented in this Google Meet now. Anyway, I am inviting Dr. Priju C P as well as all other speakers to the college when time permits. Once again, I express my gratitude to all delegates inside and outside of the college, and I congratulate Professor Davies, head of the Department of Geology, and the faculty members, Professor Kulin, Professor Ashba, and Professor Ashwadi, for this wonderful presentation of this lecture series. Once again, thank you all. Thank you.
Thank you very much, sir. Thank you everyone for joining with us for the 4-day national online lecture series and making it a huge success. Hope everyone enjoyed it and acquired more knowledge from the lectures. Once again, thank you all. Thank you very much.